Lesson 6, we're going to learn two sorting algorithms, the selection sort and insertion sort. Hopefully you've watched the two videos that I linked to. If not, you could take a minute before trying to write these. So the selection sort, all right, the basic premise is we're going to select a value from the array or the list. Could be a minimum, could be a maximum, as long as we're consistent. And then we're going to swap that value with an extreme value. So it could be the value furthest to the left or furthest to the right. If you're trying to get, least to greatest, greatest to least, that's going to affect your decision. So the selection sort we're going to go across the array, find the minimum value, and then swap that with the value farthest to the left in the array. That means that after one iteration, we'd have the smallest value in the farthest to left index. Okay, if we did that again, but we're going to ignore that first value. So we'll find the second smallest value, right? It's because we're only going to go across the array that doesn't contain that smallest value. We'll go to every other index, find the smallest value, which by definition would be the second smallest value, and we'll swap it with the second farthest to the left index. Okay, and so now we'll have the two smallest values over there, and we'll just keep repeating that until we don't need to anymore. So here's what it looks like in Java. All right, so my outer loop, it's going to go across starting at that farthest to left index, and technically you don't have to go to the last index. Okay, so you could stop one index shy. The reason is if you gave me a list of numbers and you told me that let's say there's 10 numbers, and you told me that the 9 smallest values have been sorted in the first 9 indexes, then the whole thing has to be sorted, because if I know that the first 9 are correct in relation to all 10, then the 10th number must be in the correct spot also. We call that kind of like a degree of freedom. So if I don't put that -1 there, it will still work. All right. So now, like I said, what I'm going to do is I've picked an index. In this case, I'll start with 0. That's the farthest to the left value. If I'm going from least to greatest, I want to put the smallest number at index 0. So that means I'm essentially writing like a typical minimum value type thing. And it's going to be best done through an index. So keep in mind that we're searching for the index of the smallest value. And I don't know where it is. It could be anywhere, including 0. Okay, so I'm actually going to start there. Whatever that I value is, I'm going to just assume that that's the smallest number. I'm going to go across all of the remaining numbers. Okay, so just to the right of that one, because I've already considered that one. And I'm going to see if I can find the smallest number. This loop does have to traverse to the end, because now I'm actively searching for a minimum value, and I want to make sure everybody gets a chance. Okay. And at this point, just like we've done with minimums before, if you could go into the array, in this case, a list, and you could get a number from index J that turns out to be smaller than the number you could get where you think the smallest number is, well, then you thought wrong. Okay, so we just found a better index that leads to a smaller number, and that's the one that we should track. When this loop finishes, I will have found the smallest number by index within the array list. I want that number to take over the index that I started with, which originally is going to be index 0. So I'm just going to write a basic swap right here. I'm looking to swap index I with min index. Okay. Now, keep in mind, there's a chance, because remember, that's actually where I started. So there's a chance that at the end of this, I don't need to swap. You could write an if statement in to like protect like an unnecessary swap, but in the end, we'll just go ahead and do it. All right. So like all swaps, right, we're going to make like a temporary storage. So maybe I'll say like, let's go ahead and store the value found at index I. Okay. At that point, we could set the value at index I because we've saved it. And we'll go ahead and set it with the number that comes to me from the min index. Remember, you can't use J here because J was just local to that inside loop. And then I'm going to do another nums.set. And this time I'm going to swap. I'm going to complete the swap. So I'm going to go back to where I just got that number. And this is why I had that temporary storage in swap. Okay. Remember, at the end of this line of code, you'd actually have the same number in the array list twice. Okay. And then we're going to bring back in the missing one, the one that got lost in the process. And that should do it. So what's going to happen is the first time we take the smallest number, put it at index 0. Okay. Our next loop starts a little further to the right, so it gets the second smallest number, and so on and so on. In fact, if you wanted to see it kind of in action, we could throw in an extra print statement right here. Okay. And I'll just go ahead and print out the nums array list every time. And we'll kind of see the effect of the swaps as we go through each iteration. All right. So here's your list at the start, definitely not in order. Here's our list at the end. And now it is in order from least to greatest. And if we look at all of those in between steps, all right, look what happens. The smallest value in this array list is 8. 8 and 88 swapped places. Okay, not counting the 8, the smallest number in the list is 16. Well, look what happened. 16 and 72 swapped positions. Okay, if you look at the remaining numbers in the array list, the smallest number is, I guess it's 52. 52 and 88 swapped positions, and so on and so on. When we got down to the end, okay, even though there's 10 numbers, if you count right here, it took 9 tries. Once I knew that the first 9 numbers were sorted, okay, the 10th number, it doesn't have anybody to swap with. That's why if you look at my outside loop, even though there was 10 numbers, I only ran 9 iterations, because if I know that the 9 smallest numbers have made it into the first 9 indexes, then by definition, the 10th number has been sorted also. There's really there's no one to swap with it, right? Like who could we swap this last value with? So potentially you have to pull off a swap here, which we did. Okay, in another case, you might not have to, but we had to at least give it a chance. All right, and that's what we see right here. Okay, so this is a selection sort. I'm going to do the same exact thing in the end when I write my insertion sort. I'm going to sort the numbers from least to greatest. The way that we get there is going to be a little bit different. So if we wanted to do an insertion sort, well, instead of selecting a minimum value, what we're going to do is we're going to take a value and then consider moving it further left within the array. So when we write the insertion sort, we assume that the first number is sorted, okay, in relation to itself, which doesn't make a lot of sense. And we go to the second number. So in the insertion sort, we're only going to look at 2 numbers to start. And we're just going to sort them in relation to each other. We assume that the first number is sorted, and then we try to sort the first 2 numbers in relation to each other. So in this case, like 72 and 88, I'd have to switch them. Then I'll know that when I reach the third number, that the first 2 are in order in relation to each other. And I'll try to then sort that third number in relation to them. Now, when I say sort it, really what I'm going to have to do is potentially move it further to the left, because it could be smaller than the numbers on its left, or it might not be, or it might go in the middle of them. And so I'll just sort of shuffle it along and insert it where I need to. Okay, so here's what this looks like in code. This time I'm actually going to start my outer loop at index 1. I'm trying to figure out if I need to sort numbers in relation to each other in the front of the list. Starting with 1 number wouldn't make sense here because there wouldn't be anything to compare it to. Okay, this loop's going to go all the way across the array list. It started at index 1, so it still actually runs n-1 outer loop iterations. Now, with that inner loop, I'm going to try to decide if I need to move over this value. All right, here's what I'm going to do. I'm going to take that value I and I'm going to hold on to it. Okay, so maybe I'll call it like my holding value. All right. And then I'm going to just try to decide if I need to move that value over. So actually, instead of writing a for loop, I'm going to write a while loop. And I'm going to run this while the number at the hold index. Okay, so nums.get hold, okay, is smaller than the number to its left. So the number to its left, let's see, what would that be? Okay. And if it is smaller than the number on its left, then we want to take that hold index and shuffle it down one. Okay. So we're going to keep moving that index left. Oh, I think I forgot to put a less than there. Sorry. Now, one other catch. Eventually, if I keep moving that index left, it might go off the grid. So I need to protect myself here with a short circuit and verify that hold is greater than 0. Because if I've reached index 0, the far left index, I cannot look farther to the left of it. Okay, so we start shuffling down. Now, eventually, what I'm going to do is I'm going to use this hold index and I'm going to take the number that was at index I and I'm going to put it in to this position. All right, so this is a little tricky then. Okay, so I need to hold on to this value as well. So all right. And what I want to do now is I know that I'm going to have to shuffle over to make room for where this is going to get inserted into. So I want to take nums and I want to set. Actually, I got to do this before I minus minus. Sorry. And then when we're done, we're going to take that value, the hold value, and bring it into wherever hold ended up. So we're going to say nums.set, come into that hold index, wherever it ended up, and put in the hold value. Right here, okay, we want this comparison to keep running off of the original value. So let's go ahead and put the hold value there. I think we could get away with it with based on how we're setting anyway, but it shouldn't matter. Okay. And then finally, when we're done, this sort of final insertion, that's where kind of where it gets its name from. Okay. So this is like the final insertion right here. So this is why we call it an insertion sort. We figured out like where that number belongs in relation to the numbers on its left. And then we put it into that position. If we kind of want to see it in action, we could put a print statement here as well. And we'll see the same result in the end. Like we're going to get a sorted list, but we're going to get there differently. Okay. So in both cases, I know that sometimes I think students wonder, like, well, what's going on? Like, it's always the same. Like, in the end, it's the same list. Okay. But if you look at like the middle, it's all different. So let's see what happened here in this case. All right. In the first run, I looked at those two values only. They're not sorted in relation to each other. So the 9 actually recognized that it was smaller than the number on its left, and it shuffled over that one index. So the 69 took the value's place. At that point, there was actually 2 of them in the array list. However, at that point, we reached the far left. So the 9 couldn't go any farther left. So we quit our loop and then we inserted the 9 into that index 0. Okay. On the next iteration, also notice how none of the other numbers were affected. Even though there's smaller numbers over there, like 6, okay, it didn't move yet. That comes into play on the second iteration of the loop. Now the 6 took over index 0. And so now you know that the first 3 numbers are sorted. After 2 iterations of the loop, the first 3 numbers will be sorted in relation to each other. After 2 iterations of a selection sort, the 2 smallest numbers will be at the front indexes. That happened here, but it was kind of a fluke. Okay, if we look here, after the third iteration, these first 4 numbers are sorted in relation to each other, but I don't have the first 4 smallest values. I also don't have the first 3 smallest values like a selection sort would. At this point, we actually encountered a 91. What's interesting there is that 91 was already sorted in relation to the numbers to its left. So our while loop didn't even run a single time right there. The insertion sort potentially is going to take less iterations of the loop because the while loop might not fire every single time. All right, that 59 has to sort in relation to the other numbers. It didn't go all the way to the front of the list. What happened with that 59 was the 91 moved right, the 89 moved right, the 69 moved right, and then the 59 took over index 2. But it didn't keep going to the left, right? It didn't take over index 1 or index 0. It inserted itself into index 2, and the other numbers moved over. Since I was using an array list, there's probably some other ways that I could do this with like add and remove methods. But if you look at an array, it's very much how I'm doing it here. And then we kept going, and eventually we got to the end. If you look at, say, the 8th pass, you know, I guess this is the 8th pass. I know that the first 8 numbers will be sorted in relation to each other. What's interesting, though, is that 39, see how it's been in that column? We haven't even looked at that number yet because on the 8th pass of the loop, we have only reached I equals 8. And we have not reached index 9 anywhere. We're only looking to the left, right? See, it's all -1, minus. There is no +1. The loop isn't going further to the right. Okay. Let's say that we wanted to put in some counts to see which of these is giving us, more iterations. If I wanted to put in some counts, I'd have to kind of structure it so that it was on the interior loop. All right. So maybe like right here, I'll say int count equals 0. And then somewhere in here, don't put it on your outside loop. It's the inside loop that's really determining overall how many iterations you're looking at. And I'll do something like that right here. Yesterday, we were using a return method. This is a void method. So we can just put our print statement right at the end. Okay, so I can just put a print statement right here that gives me the counter. And I'll just say something like I did yesterday. I'll say total iterations equals, and then I'll get the count final value. Now, with the selection sort, you would notice that no matter how many times you ran this, you'd get the same value every time. Okay. For the insertion sort, that's actually going to fluctuate a little bit based on how many times that while loop needs to run. If we wanted to, we could do something a little bit more grand scale. Okay. Like for right now, I have 10 random numbers from 1 to 100. If I took this up to say maybe 10,000 random numbers from 1 to 100,000, if you do this, I definitely recommend you turn off these print statements here, though, or else your screen's going to get pretty crazy. You'd see 10,000 prints in both cases. We don't want to see that. So let's just see what happens here. Now, 10,000 might not seem like a really large value. I thought I turned off the print statement. You know, I just had to print all those numbers. Okay. I should turn off all the. Let me do that again. Sorry. Let me just turn off all the print statements here. Okay. So let's just see the count required for each. Even though I wasn't printing with each iteration, I was still printing list of 10,000 values. So let's see what happens this time. Okay. So for my, oh, wow, look at that. For my selection sort, 49 million, almost 50 million iterations. So to sort 10,000 numbers took almost 50 million iterations of the loop. And for the insertion sort, about 25 million. Um, you can read a little bit more about the operating times of these loops, but this is not considered efficient. Okay. We can do better than this. We could probably get it down into the 20, 30,000s with some more effective algorithms. And, you know, you could even try, like, you got to be careful. If you put a number here that's too big, okay, your loop, your replet might time out. It might run out of memory. It might also get confused and think that you've written an infinite loop and kick you out. But you can see here for yourself. I mean, it's paused right now because it's running so many iterations that even though I have a fast computer, even though I have a fast internet speed, it still is struggling with this large scale of operations. We're probably talking about 500 million iterations for this sort. So I'm not even sure if I'm going to get an answer or not. It doesn't look like we're going to. Um, I think we can maybe just end the video here. I'll tell you if I got something in class. Oh, we did. All right. We've got, wow, 700 million. Yeah, 700 million iterations for the selection sort. The insertion sort's probably going to be about half of that. But I mean, if that took 30 seconds, then we're talking like a 15-second sort. So yeah, if you don't write good, efficient algorithms, you can see quickly how this stuff can take a long time. But like I said, there are more efficient algorithms that we can use. Oh, you know what? So that's 700 million. So that's not even accurate because that was an integer rollover issue. We see that here. So I'm not even sure how many of these took. I'd have to use something like a double or a big integer.